Now, before Christmas, we had a look at complex numbers in terms of what they are, in terms of how to add them, subtract them, multiply them and divide them, and we stopped short in terms of turning a rectangular form complex number into a polar form complex number, and that's what I want to do in terms of trying to get this chapter finished. So we should try and get this chapter out of the way as quick as we possibly can. Give it a week, maybe no more than a week, and then we shall move on to maybe sequences and series, or something that's going to give us a bit of a, I suppose, content for paper 2. So complex numbers, if you remember what they are, first and foremost, a complex number is nothing more than a number that has a real part and an imaginary part. Okay, even if the values of the real and the imaginary are 0, they still have to have both parts in order to be a complex number. So a complex number, and you'll see it here yourselves, is one that is written in the form of a plus bi. Now, just to be sure that people understand this, a and b, they're the values. Notice I have them in red and blue. I don't have the I marked in red or blue because the value of the real and the value of the imaginary are the numbers that we're going to be referring to, not really the I. Okay, so A is the value of the real part and B is the value of the imaginary part, and together a real with an imaginary gives us a complex number. So if you take, for example, the number -7, -7, yes, is a real number, but in complex form it's -7 plus 0i. Likewise, 4i is an imaginary number on its own, but in complex form it's 0 plus 4i. So in other words, to get it into a plus bi, it must have both parts. Even if one of those parts is 0, it must be stated as such. Okay, every complex number has two parts, as we've said already, the real and the imaginary. All right, so the real numbers belong to a set in themselves. The imaginaries now belong to a set, and I just want to talk about these in case you've forgotten. What are the imaginary numbers? The imaginary numbers are numbers that are the solutions to the square root of a negative number. So square root of -4, square root of -9. The problem in the real sphere is we can't get the square root of a negative number because there are not two real roots that are identical to one another that will multiply back to -4. So instead, what we do is we take the positive version of 4, so the square root of 4, and then we multiply it by the square root of -1. And because the square root of -1 doesn't have a real value as an answer, we simply call it I. So the way around trying to get the square root of a negative number is to get the square root of its positive aspect and stick the letter I afterwards. And what's I? It's nothing more than the value of the square root of -1, which we can't describe in real terms, so we put it down as an imaginary number. All right, so 4 plus 2i minus 7 plus 9i, etc., etc. That's a real and an imaginary together, which will give you the set of complex numbers. The letter Z, now small z, I want you to remember that. The large Z that we use like this, they're integers, okay? But the small z, like Z1, Z2 and so on, they represent the complex numbers. So Z1 would be the first one in this case here, -4 plus 3i, and Z2 would be 2 plus 3i, and so on. So, before we move into, I suppose, the polar form of a complex number, there's three things we have to look at in terms of the transformation of a complex number, all right? One of them is the transformation through addition. Now, I want you to take this example here. We have Z1, Z2, and Z3, okay? When I add Z1 to Z2, I get Z3. But really, in essence, what's happening is that when I take Z1 and I add on Z2, what I'm doing is I'm taking Z1 on the same journey that I take in order to move from the origin to Z2. So if you take it this way, to get to Z2, I start at the origin, I move out 4 digits, and I move up 2. Okay? Now, if I add that triangle to Z1, what happens? I move out 4 units, and I move up 2. See that? So out 4, up 2. That's going to bring me to Z2. So if I add Z2 to Z1, I go out 4 and up 2, which brings me to Z3. So what I'm really doing is I'm bringing Z1 up to Z3 through the addition of Z2, sliding it up to Z3 through Z2. And another way to say that would be this way. To take Z1 to Z3, I simply follow the journey of this red line to go from 0 to Z2, if you want to take it in terms of the rectangle that's present, okay, or the parallelogram in this case. So from 0 to Z2, if I'm at Z1 to Z2, I'm going to move this way to Z3. Now likewise, we can say the same thing of Z2 plus Z1. If I start at Z2 and I add on Z1, first of all, how did I get to Z1? Starting at 0, out 1, up 3. Let's do the same thing to Z2. Out 1, up 3. I end up in exactly the same place, Z3. Okay, and again you could say the same thing if you want to in terms of the parallelogram. If I want to take Z2 and add on Z1, you follow this line. See that? So from 0 to there is Z1, so I do the same to Z2, which brings it this way. So I hope you can see that addition of two complex numbers is nothing more than a translation through addition. You're translating Z1 up to Z3 by adding on Z2, or you're translating Z2 up to Z3 by adding on Z1. But that's the translation through addition. So Z1 plus Z2 equals Z3. The position of Z3 on the Argon diagram is said to be a translation of either Z1 or Z2 by addition. Okay, so 0 to Z1, Z2 to Z3. Or, as I told you already, the other one, 0 to Z2 and Z1 to Z3. Either way, we end up in the same place. So when you add two complex numbers together, it's what we call translation of a complex number by addition. Notice how Z1 when added to Z2 moves horizontally by 4 units and then vertically by 2 to the new position of Z3. So, as I told you, Z1 plus Z3 plus 4 plus 2i is 5 plus 5i. That's how we add complex numbers. That came from the previous part of the chapter we did before Christmas. The second one I want to look at is what we call the transformation of stretching or contracting. So if you take Z1, Z2 and Z3, okay, Z1, as we can see here, is the number 2 plus 4i. Okay, Z2 is the number 2 plus 3i, and Z3 is the number minus 1 plus 2i. Now, what's happened is they've been stretched by some factor called a. See that? Now, in order to stretch a complex number away from the origin, the value of a obviously has to be greater than 1. That makes perfect sense. If you multiply by 1, it stays the same. If you multiply it by anything greater than 1, it starts to stretch away from the origin along that same straight line. So Z1 has gone from being 2 plus 3i into being 4 plus 8i. Z2, sorry, that's Z1. Apologies there. Take that out. Start on Z1, the easiest one to use. So Z1 has gone from 2 plus 4i up to 4 plus 8i. Okay. Z2 has gone from 2 plus 3i up to 4 plus 6i. And lastly, Z3 has gone from minus 1 plus 2i as far as minus 2 plus 4i. Now it's very clear to see 2 plus 4i up to 4 plus 8i. That's multiplied by 2. That's been multiplied by 2. And that's been multiplied by 2. So in this situation here, we've discovered that a is 2. Okay? And when you multiply any complex number by a real number greater than 1, we get a stretching effect. It'll continue to move away from the origin along the same straight line to the factor of the multiple. So it'll be twice the distance or 3 times the distance, whatever it's going to be that you're multiplying by. Okay, that's the first thing. The second thing I want you to think about is this. How would I get Z1, Z2 and Z3 to contract towards the origin? If multiplication by a number greater than 1 causes a stretch away, then obviously multiplication by a real number less than 1 is going to cause it to contract. So let's take the same numbers again. Let's take Z1. Z1, as we already said, is 2 plus 4i. Okay. Z2 is 2 plus 3i. And Z3 is minus 1 plus 2i. Now, let's take a number that is less than 1. Let's take the most popular number that's less than 1. Let's take a half. And let's multiply each of these by a half. What do we end up with? A half of 2 is 1. A half of 4i is 2i. A half of 2 is 1. A half of 3i is 1.5i. And a half of minus 1 is minus 0.5. And a half of 2 is 1i. Now let's plot those numbers. So 1 plus 2i. 1 plus 2i is there, which is exactly halfway. It's contracted. It's gone down this way. See that? Z2, which was 2 plus 3i, has become 1 plus 1.5i down here, and again a contraction by half. And lastly, what was minus 1 plus 2i has contracted down to plus 1 and minus a half, which is just there. So again, we get that contraction. So what I need you to remember is this. When we take a complex number and multiply it by a real number, we will either get stretching away if the real number is greater than 1, or contraction towards the origin if the real number is less than 1, i.e. fractional less than 1. Okay, so if we take a complex number, as we say a plus bi, and multiply it by a real number, two things can happen. If n is greater than 1, it will stretch away, and if n is less than 1, it will contract. Okay, in this case, as I've showed you already and I've worked it out for you, a is 2, since z1, z2 and z3 have all stretched twice as far away from the origin. And I asked you a question, predict what would happen to z1, z2 and z3 if a was equal to half, and the answer is they would move down towards the origin by half the original length. So z3 would contract, z1 would contract, and z2 would contract, all by half their distance closer to that particular origin. That's the second thing. And the last transformation we have is what happens when I multiply a complex number by I itself. Okay, so if I take, for example, any complex number multiplied by I. So I want to think about this. If I multiply a complex number by I, let's take this one here. Let's take z1. z1 is 2 plus I. Let's multiply it by I and see what happens. We get 2i plus I squared. Now, plus I squared is better known as minus 1. And because real numbers should really always go in front of the imaginaries, it's minus 1 plus 2i, which happens to be here where z2 is. Do you see what's happened? z1 has rotated to z2. In fact, the rotation that's taken place is exactly 90 degrees. So therefore, when you take a complex number and multiply it by I, there will always be a 90-degree rotation anti-clockwise. Now, if multiplication by I gives an anti-clockwise rotation of 90 degrees, just guess for a moment as to what would happen if you were to multiply a complex number by minus I. I gives an anti-clockwise rotation of 90 degrees, so therefore minus I would give a clockwise rotation of 90 degrees. And let's just verify that. So again, we have z1, which is 2 plus I, and this time I'm going to multiply it by minus I. Minus I times 2 is minus 2i, and that gives me minus I by plus I, which is minus I squared, and minus I squared is plus 1. So I get 1 minus 2i, which happens to be down here where z2 is. In this case, notice that the rotation is 90 degrees clockwise. So minus I is 90 degrees anti-clockwise. Sorry, I should say, and minus I is 90 degrees of a clockwise rotation. So the three of them again, when I add a complex number to a complex number, I will get a translation through addition. If I multiply a complex number by a real number, providing the real number is greater than 1, I'll get a stretch away from the origin. If the real number is less than 1, fractional, it'll contract towards the origin. And lastly, if I take a complex number and multiply it by I will get an anti-clockwise rotation of 90 degrees. And if I multiply it by minus I, I'll get a clockwise rotation of 90 degrees. So when we talk about the rectangular form of a complex number, what do we actually mean? The rectangular form is the form of the complex number that is a plus bi, okay? Where a and b are the values of the real and the imaginary. Now I want you to think about this. If you take a plus bi, there it is, and you take the values of both, a is the real value, so the real value is a, and the imaginary value is b. These two operating together give me a couple. They give me a coordinate, okay? Which means that the rectangular form of a complex number can be plotted on what we call the Argand diagram. And we did this before Christmas, but it's just a refresher. And the Argand diagram is an axis that replaces the normal x and y by the real and the imaginary. Because if you look at a complex number, the first part is the real part and the second part is the imaginary. In coordinate geometry, when we're dealing with points, the first part is x and the second part is y. So in this case, the x-axis is replaced by what we call the real axis, and the y-axis is replaced by what we call the imaginary axis. So we end up getting something similar to this, okay? The real axis is what used to be the x-axis because it's first, the real part is first, and then the imaginary axis is what used to be the y-axis. So here's a very simple question. Plot the point -3 plus 5i on the Argand diagram. First of all, take it as a couple, -3, 5. You just take the values, okay? So you want to do it that way. Back 3 units, because it's -3, and up 5. So we end up here. Now, that is the point -3 plus 5i. But something very interesting happens when I plot that point. Because if you remember before Christmas, one thing we did say was that every complex number has a unique relationship with the origin. And that unique relationship between a complex number and the origin is called the modulus, okay? The distance away from the origin. So if I was to fill that modulus in there like that, this is what I get, like that. Whoops, a daisy. Can't do a straight line, but you get the idea. That's it. Now what is that? Well, let's see. How did I get to -3 plus 5i? I moved back 3 units and I went up 5 units. What have I just developed? I've just developed a right angle triangle in which the base is back 3 units, up 5 units, and we end up then with this hypotenuse, which is the modulus of the complex number. Now, I want to take a little step further. If I was to pin this complex number on the origin and spin it around, you can all see what shape I'd get. I'd get a circle, okay, like that. Circle that would spin around like this. And that means that the distance between there and there, which is the modulus, would also be called the radius. Now when we're moving into polar form, we have to refer to the modulus as r, which is the radius of the circle that would be formed if I was to take that complex number on a journey around the origin, pin it on the origin and spin it around, okay? So the modulus is now the radius. Of importance also is the angle that is made between the hypotenuse and the x-axis. Now, I hope you remember when we were doing trigonometry that in every quadrant except the first, we refer to the angle made as alpha, not theta. Okay? The only place where theta can be found directly is in quadrant 1. In quadrant 2, 3, and 4, we have to refer to the angle being used as alpha, and then work out theta by either adding it or subtracting alpha from 180 or from 360. Because don't forget, the angle I'm really interested in is that one. That's the angle I'm interested in because I always have to make reference to 0 degrees, which is the positive aspect of the right hand side of the x-axis. We always start counting from there. Okay, so that's two things I need you to remember. First of all, when you plot a complex number, you form a right angle triangle. In the right angle triangle, the hypotenuse is the modulus, which is also the radius of the circle that the complex number would form if it was to spin around the origin. And secondly, the angle that the modulus makes with the x-axis is called the argument. A-R-G-U-M-E-N-T, the argument. Okay, the argument, this angle here, theta, is the argument. So that one there is the argument. And notice that when we're using alpha, alpha is not the argument. Theta is always the argument. Alpha will be the one that will allow you to calculate theta if you're in the second, third, or fourth quadrants. And I'll explain a little bit more about that as we go on. Okay, so the position, as we said, forms a right angle triangle, and the triangle is the basis for writing the number in polar form. So let's take a look at this. What is the polar form of a complex number? Well, the polar form of a complex number is the complex number not written as a plus bi, but written in terms of the relationship of the modulus and the angle that it makes with the 0 degrees, or the right hand side of the x-axis, which we call the argument. Okay, we have to work out both of these. We've got to work out the modulus, r, and then we've got to work out theta, which is the angle that the complex number makes with 0 degrees, the right hand side of the x-axis. And I'm going to demonstrate that now with two examples in a moment. R is the modulus, as I said already, and theta is the angle the triangle makes with the positive aspect of the real axis. It's also known as ARG. And you might see it written sometimes that way in the exam. They won't write out the word argument. They might just write A or G, which you know then has to be the angle that the complex number is making with the 0 degrees or the right hand side of the x-axis. Okay, so let's take this question here. Write minus 3 plus 5i in polar form. Now there's 3 steps to this. Number 1, plot the point. So minus 3, that's back 3 and up 5. So there we are. Okay, there's minus 3 plus 5i. What does that complex number do? It makes a triangle, like so, with the origin. Okay, and in that triangle, what do I know? The base is 3 and the height is 5. Okay, now it goes back 3. You see the minus 3? It's back 3. You're going back 3 and you're going up 5. But because it's distance, we still give it a positive 3 when we're talking about the length of the line. And then, because I'm in quadrant number 2, I'm going to call that alpha, not theta. So the 2 things I want to work out are r and theta. So let's work it out. R is the hypotenuse of this right angled triangle. So therefore r squared is equal to 5 squared plus 3 squared. R squared is equal to 25 plus 9, which is 34. Therefore r is the square root of 34. Now, I don't think you can simplify that. I have my trusty square root of 34 is the square root of 34. Stays the same. Okay, so there's r. Keep that highlighted in front of you. And now I have to work out the angle alpha. Okay, now alpha, as we can see already, is in this triangle where 5 and 3 are the opposite and the adjacent. Don't ever use the hypotenuse for this. Always use the opposite and the adjacent, which means if I'm using 5 as the opposite and 3 as the adjacent, I'm using the function tan as the opposite over the adjacent. So alpha, therefore, if I want to get rid of tan, I shift tan. So it's tan minus 1, 5 over 3. And your trusty calculator will tell you that you shift tan of 5 over 3 becomes 59 degrees. So alpha is equal to 59 degrees. But alpha is not our argument. Our argument is the angle that's made with the 0 degrees of the x-axis. So therefore notice that theta is 59 degrees short of 180. So therefore theta is 101. Oh, sorry, 100 and what's I 59? 180 minus 59. 180 minus 59, and that comes out as 121 degrees. 121. 121 degrees. So what's the polar form? It's r cos theta plus I sin theta. Now sometimes you might see it written this way, or cis theta, and it's nice for you to remember that as a way, kind of a shorthand way to remember. R times the cos of the angle plus I times the sine of the angle. So this is going to become r, which is root 34, times the cosine of the angle, which is 121 degrees, plus I times the sine of the angle, which is 121 degrees. Now don't worry about using degrees. That's perfectly fine. It's allowed and it's doable. I'm not going into radians. I don't do radians. I work in degrees only, as you already know. So r cis theta. That's just a shorthand way to remember that it's the modulus multiplied by the cos of the angle plus I times the sine of the angle. So if you want to remember that, r cis theta. That's just a nice way to remember how to get a number in polar form. All right. So when I take r as root 34 and theta is 121, I put it in here. Root 34 times the cosine of 121 plus I times the sine of 121. That's it. Okay, so let's take 2 examples here before I set you away to do some yourselves. Write the following complex numbers in polar form. 3 plus 3i. Step 1, plot it on the Argand diagram. Out 3, up 3. So there's your point. 3 plus 3i. Remember what I said to you? Out 3, up 3. So form your triangle then by putting in the hypotenuse from the origin to the complex number. Call that r, and because we're dealing in the first quadrant, that is going to be theta. That's the only time we can actually take the angle as given. Okay, and in this case I've got to work out these two. So r is the hypotenuse. R squared equals 3 squared plus 3 squared, because don't forget it's 3 out and 3 up, okay, which gives me r squared equals 9 and 9, 18. Therefore r is equal to root 18. And on your calculator, if you check it carefully, there is a way, simpler way, root 18. It comes out as 3, and you can see that 3 root 2, okay? So just be careful that you always check for the simplest form of that surd, 3 root 2. So now I know what r is. R equals 3 root 2. So put a square around that because you're going to use it later on. The next thing I've got to do is find theta. So if I want to find theta, what do? Take the opposite and the adjacent. Use the function tan with theta equals the opposite over the adjacent. So therefore tan theta is equal to 1. And if tan theta is equal to 1, again shift tan out of there. Theta equals the inverse tan of 1, which is 45 degrees. So now I can use theta in here. Remember, or cis theta, or 3 root 2 times the cos of the angle, cos 45 degrees, plus I times the sine of the angle, sine 45 degrees. And that is 3 plus 3i in polar form. Let's do one more. Let's do the 2 minus 2 root 3i. So let me just clear that. Okay, so 2 minus 2 root 3i. First of all, out 2 and down 2 root 3. Now, root 3 is about 1.7. So 2 1.7 is about 3.4. So let's say about 3.5 if you want it, just to be, because it's only a sketch. So out 2 and down about 3.4. It's about there. Okay, so out 2 and down 3.4 gives me this triangle here. Okay, now that's 2 and that's 2 root 3. So out 2 and down 2 root 3. See that? So out 2 and down 2 root 3. That's r, and this time that is not theta. Because I'm in quadrant 4, that's alpha. So we're going to have to use alpha to get theta later on, which we will do. But let's work on the easy part first. Let's get r. R squared equals 2 squared plus 2 root 3 to be squared. So in other words, you're going to square these two sides and add them together. That's 4 plus 2 root 3 to be squared on your calculator if you have to. But 2 squared is 4, root 3 squared is 3, 4, that's 12. That means that r squared equals 16. Lovely. R is equal to 4. Good. So there's r. So r is 4. Now, I want to find alpha. So to get alpha in this triangle, I'm going to use the opposite and the adjacent again. So tan equals the opposite, 2 root 3 over 2, which means that the tan of alpha is equal to the 2's will cancel, root 3. And to get alpha on its own, I simply shift tan over the other side. So alpha equals tan minus 1 of root 3. And as far as I remember, the inverse tan of root 3, I hope, whoops, is 60 degrees. What I'm doing there, talking to myself, is 60 degrees. I'm just going to check that on the calculator to make sure. Inverse tan of root 3, shift, tan, root 3. Never guess in maths. You can't afford to guess. Is 60 degrees. Okay, and there it is. However, that is not theta. Don't forget that polar form is C, is R, C, I, S, theta. R and theta, they're the two things. How do we work out theta? Well, alpha is 60, and it's 60 degrees short of 360, which means that the angle going from there all the way around to here is actually 300 degrees. So therefore theta is 300 degrees. And that means, if I follow this thing up here, that the polar form is r, which is 4, times the cos of the angle, cos 300 degrees, plus I times the sine of the angle, 300 degrees. And there's 2 minus 2 root 3i in polar form. Okay, now I'm going to leave you with these to do. So I'm going to ask you to pause your video now, work on these ones, try and work them out, draw the triangle, plot the point, get the length of the hypotenuse, call it r, then depending on what quadrant you're in, work out either theta if it's in quadrant 1 or alpha if it's in the other 3, and then work out the argument and bring them back into what we call, there it is there, r times cos theta plus I sine theta, or if you want to, an easy way to remember, r cis theta, meaning r times the cosine of the angle plus I times the sine of the angle. Just makes it easier for you to remember. Okay, so pause and off you go. Now, providing you've done those properly, and I'll give you the solutions, we'll go through them, the solutions we put up in a second video. How do we move backwards? So if we know how to turn rectangular form to polar form, how do I move from polar form back to rectangular form? And the answer is through your trusty calculator. That's the only thing you have to use in terms of turning polar form back to rectangular form. So it's very, very simple. So if they give you something highfalutin and something complicated like that, for example, write root 3 cos 7 pi over 6 plus I times sine 7 pi over 6 in rectangular form. What do? You write down root 3 and then you go to your calculator and you ask your calculator simply, what the hell is the cos of 7 pi over 6? 7 pi over 6. Don't forget pi is shift the bottom, but times 10, so it's down there, and that comes out as 0.997. 0.9976. Okay, plus I times the sine of 7 pi over 6. So we now want the sine of 7 pi over 6. Pi over 6. Oops, sorry, apologies, my mistake. I forgot something, and I told you about this already. What have we got to do? We've got to turn the pi into 180. So first of all, you write this in terms of degrees. I knew there was something funny there. So that's going to be 7 times 180 over 6 plus I times the sine of 7 times 180 over 6. So you turn it into degrees first. You can't use radians when you're using your calculator unless you turn it in. No, not going to interest in that. So root 3 times the cosine, 6 into 180 goes 30 times, and 30 times 7 is 210 degrees, plus I times sine 210. Now it's much easier. Now you can use your calculator. So it's root 3 times cos 210, cos 210, whoops, cos 210 comes out as minus root 3 over 2. It's much better. I knew there was something wrong with doing the previous calculation. And then sine 210 comes out as minus a half. Okay, so therefore, what's it going to become? Root 3 by root 3 is 3. So that's minus 3 over 2. Plus and minus is minus root 3 over 2i. And that's it. That's it in rectangular form. That's all you've got to remember, because the I is in there as well, I times. So that's it. And there is your rectangular form of your number. So keep in mind what you do. The first thing you do is you turn your radians into degrees. And then once you have them in degrees, you simply use your calculator to work out the cos of 210, the sine of 210, and don't forget then to multiply both of them by root 3, or the argument, or the modulus that's at the start of the polar form complex number. So turn your radians into degrees, then get the cos and sine of that number of degrees, and then multiply it by any number that is at the start of that polar form. Okay, so keeping in mind that pi, when used directly with trigonometric functions 180, this becomes 3 times cos 210, I times sine 210, and using the calculator you get, as I had a moment ago, minus 3 over 2 minus root 3 over 2i. Again, pause and off you go with these. I want you to take a look at those and try and turn these from polar form back into rectangular form. And again, I'll put the solutions up later on if you've got a difficulty with them. Pause and off you go. Okay, final two bits to this thing. How do we multiply polar form numbers and how do we divide polar form numbers? Well, first of all, multiplication of polar form numbers, it's actually quite easy. When you're multiplying two polar form numbers, don't forget that both of them will have what we call a modulus at the beginning, okay, and both of them will have an argument, okay, cos of theta, sine of theta, and so on. So what we do is when we multiply two complex numbers together in polar form, we multiply the moduli and we add the angles. Simple as that. Multiply the moduli and add the angles. So just to take division, it's the opposite. If you're multiplying two polar form numbers together, you multiply the moduli, you add the arguments. So therefore, if dividing, what do? You divide the moduli and subtract. I remember telling you at the start of 5th year, multiplication and addition are intrinsically related. Subtraction and division are intrinsically related. Okay, so whenever you have multiplication is only fast addition. So you multiply the moduli and you add the arguments. For division, you divide the moduli and you subtract the arguments. So let's take an example. If these two polar form complex numbers are Z1 and Z2, then when you multiply Z1 by Z2, you multiply R1 by R2 and you add θ1 to θ2. That's it. And likewise, when you're dividing them, you divide R1 by R2 and you subtract θ2 from θ1. And it must be in that order. You keep the order in terms of the way the numbers are given to you. Now again, let's take an example. If Z1 equals 3 times cos pi over 6 plus I times pi over 6, and Z2 is 4 times cos pi over 3 plus I times sin pi over 3, what do they want you to do? They want you to multiply the two and divide the two. So let me go through this with you, then I'll give you some to do yourselves. First of all, multiplying Z1 and Z2. What do they tell you to do? Multiply the moduli and add the arguments. Now the first thing I notice here is again pi. We don't use pi, we turn them into degrees. So I'm going to put these down as 3 times the cosine of 180 divided by 6, 30 degrees, plus I times the sine of 30 degrees if you wish. Okay, and then over here 4 times the cosine of pi over 3, that's 60 degrees, plus I times the sine of 60 degrees. Now the one thing I will say about this is when you're adding pi over 6 to pi over 3, you can use your calculator. You can use it for that, but again, might be just easier to turn them into degrees and leave them at that. So let's do the first one. Multiply the two. Answer. You multiply the two moduli, 12, and then you add the arguments. 30 and 60 is 90, plus I times the sine of 90. That's it. That's how you multiply two polar form complex numbers. You multiply their moduli and you add their arguments. Okay, and then the second one, Z1, that's Z1, Z2. Z1 over Z2. Now it's important that the order is kept right here. So for Z1 over Z2, what do? You divide the moduli. So it's 3 over 4 times the cosine of the difference between the two. So that means you've got your 30 minus 60, which is minus 30 degrees, plus I times the sine of minus 30 degrees. Now don't worry about the minus, because if you think about it, what's minus 30? Minus 30 is 30 degrees backwards, which in one sense is 330 degrees going that way. See? So you can write that down as 3 over 4 times the cosine of 330 plus I times the sine of 330. And that's it. So for multiplication of two complex numbers, you multiply the modulus and you add the argument. Okay. For the division of two complex numbers, you subtract the moduli, divide the moduli and you subtract the arguments. Simple as that. Okay. And again, I've put this out here for you. And you notice what I've done here is I've left it in terms of pi. If you tap into your calculator, pi over 6 plus pi over 3, the calculator will tell you pi over 2. And likewise, pi over 6 minus pi over 3 is minus pi over 6. It's just a little more difficult to turn back into degrees. So if you want to work in degrees like I do, feel free. All right, let's take one of each of these and then I'll leave you with the rest to do. I'm going to do the first one here. So write the following in polar form. These are being multiplied by one another. What's the rule? 2 times 3 is 6 times the cosine of pi over 8 plus pi over 12. Do you know what? Just use your calculator. Turn on your fraction. Shift pi over 8 plus pi over 12. Fraction pi over 12 equals 5 pi over 24 plus I times the sine of 5 pi over 24. That's it, finished. Okay, so that's that one done. I'm going to leave you the second one to do, and then I'm going to do the last one down here. Division. What do? You divide the moduli. 12 divided by 4 is 12 divided by 4 is 3. Oops. 12 divided by 4 is 3. Now, you subtract the arguments. So it's the cosine of, and let's put in pi over 7, so fraction, pi over 7, oops, fraction pi over 7 minus fraction pi over 14, and that comes out as pi over 14. Okay, so pi over 14 plus I times the sine of pi over 14. That's your multiplication division. I'm going to leave you with those two to do, so you can do those two now. Again, pause, try those two, work them out. If you have any difficulties, we'll go over them when we're going through the solutions at the end. Okay, so I'm going to leave you as well with these ones. Write each of the following in polar form. So you've got 3 multiplications and you've got 4 divisions. Okay, if you can multiply polar numbers and divide polar numbers and then transform a complex number by means of additive translation, multiplication of a real number, multiplication by I, and so on, then you'll have no difficulty with these. The only little difficulty in this one might be whether you keep pi over 4 in terms of radians pi over 4 or change it into degrees. I always work in degrees, and people do tell me it's easier, so feel free to work in degrees if you wish to do so. Off you go. At the start of the next class we will go over some of these if you have any difficulties with them, and then we'll carry on, move on to the next section.